Hello everyone, welcome to 8.1 Energy Sources video 4 of 4. This is the last installment for the 8.1 video series. This is the slide that we left off on last time. We investigated energy transformations involving wind, and we also looked at energy from gravitational potential energy sources. So when you extract water that comes from a dam, when you have energy coming from a tidal barrage, so sun and moon driven systems, and this was the associated Sankey diagram we looked at. So let's move on to our stuff for today. So practice. A reservoir for a hydroelectric dam is shown. So of course it's a simplified geometrical structure. It's a rectangular prism just to make the calculations a little bit simpler. Part A, calculate the potential energy yield. Right, the whole idea behind the sun-driven hydroelectric dam is that the water falls from a higher elevation to a lower elevation. And in doing so, it gains speed, it gains kinetic energy. The faster it goes, the faster the turbines rotate, the more electricity is generated. So let's figure out the potential energy yield. Now, potential energy, that's gravitational potential energy in this context. And gravitational potential energy, we know the formula for that. So let's go to our page here. Okay, so gravitational potential energy is mgh. Okay, so mass times gravitational acceleration times h. Now let's just pop back to the slides for a second. G is 9.8, that's pretty straightforward. H, the height. Okay, so what this tube here in the picture is representing is effectively how the water is going to be draining down. Just a simplified picture again. Now you have this height here of 75 meters, but you also know that the height or the depth of the water is 50 meters. So we don't use 75, we don't use 75 plus 50, we take an average of the 50 distance and we do 75 plus half of 50. Excuse me. So we do 75 plus 25, so therefore on average the water is falling through a height of 100 meters. Okay, excuse me. So H, this is going to be the 75 meters plus 50 divided by 2 meters. So that's 100 meters. Now your G value, I mean, that's the acceleration due to gravity. Okay, so G is 9.8 meters per second squared. If you look at the completed slides afterward, you're going to see that the value of 10 is approximated. That's fine, but 9.8 is the exact value. And so now we have to find the mass of the water. And really all we're given is the dimensions. So let me just quickly sketch out here what we're given. And you have the slides in front of you as well. So we know that we have a 2,500 meter width. I have a 50 meter depth or height, and I have a 1,700 meter length. Okay. I know how to find the volume of this box. That's probably the first thing that you think of. I know how to find the volume. Well, is there any relation between volume and mass? And there is. It involves density. So density is mass per unit volume. So there's that Greek symbol rho, R-H-O. Okay, so that means density. So mass I'm going to find by taking density and multiplying by volume. Volume. All right, so volume is going to be length times width times height. So I'm just going to multiply all these values together. So 1,700 times 2,500 times 50. Excuse me. So grab your calculator. 1,700, everything is in SI units, so that's good. And these numbers are huge because after all, this is water contained in a dam. It should be large. So this is about 2.125 times 10 to the 368. Okay, and that's cubic meters. All right, now for the density of water, although it's not given in the question, this is something that is expected that you could look it up. And since we're dealing in SI units here, it is expected that you would look it up in SI units or at least be able to convert it to SI units. So the density we're going to use here is 1,000 kilograms per cubic meter. Okay, so that's the density of water. All right, so given those two pieces of information, we're going to go ahead and find the energy yield or the potential energy yield. So EP, so it's equal to M times G times H, and I said that M was equal to rho times V. So that's rho VGH. All right, so rho is 1,000. V is this value right here, 2.125 times 10 to the 8. G is 9.8. And H, we said the approximate value of 100 is what we're going to use. Okay, so grab your calculator. So 1,000 times 2.125 times 10 to the 8 times 9.8 times 100. All right, so 2.08 times 10 to the 14. So about 2.1 times 10 to the 14. And the units are joules. Energy is a scalar, so no direction necessary. Okay, so this was part A of this example. Okay, so let's go back to the slides and continue. The reason why this value is a little bit different than what we got is because in the slides, the calculation is done using the G value of 10, not 9.8. To be exact, 9.8 is better to be used, and on your exam, please use 9.8, not 10. All right, part B, if the flow rate is 25 cubic meters per second, what is the power provided by the moving water? All right, so 25 cubic meters per second, that's the amount of water flowing down this pipe. You know the total volume of water contained in the reservoir. So let's go back to our sheet here. So now we're in part B. I know the flow rate is 25 cubic meters per second. And I know that I have a total of this much water in general. So the volume is 2.125 times 10 to the 8 cubic meters. So just looking at those two pieces of information, I already know that I can figure out how many seconds it's going to take to drain the entire reservoir of water. Okay, so if I want to get the unit of time out here, I'm going to have to take meters cubed and divide it by the meters cubed per second so that the units I get out are seconds. So I'm going to take my 2.125 times 10 to the 8 cubic meters, and I'm going to divide it by 25 cubic meters per second. All right, let's see what we get. 2.125 times 10 to the 8 divided by 25. So that's 8.5 times 10 to the 6 seconds. Okay, so how is this going to help us? Well, we're looking for power. Power is energy per unit time. So we saw that in grade 11 physics, and you're seeing it again now. So this is T. Power is what we're looking for. Again, power is energy per unit time. The energy that the water has stored in the reservoir is stored in the form of gravitational potential energy, which we just calculated in part A. So this is EP. So we're going to just plug that in. So 2.1 times 10 to the 14 joules. Divide that by 8.5 times 10 to the 6 seconds. A joule per second is a watt, so that's the unit for power. All right, here we go. So 2.1 times 10 to the 14 divided by 8.5 times 10 to the 6. So we get 2.47 times 10 to the 367. So 2.47 times 10 to the 7. Now this is watts. Now what we can do is we can call that about 24.7 times 10 to the 6 watts. Now the reason I did that is because the times 10 to the 6, that's a common prefix. Okay, so that would be mega times a million. So this overall is about 25 megawatts. Okay, so there's the answer to part B. Right, so hopefully that's okay so far. Let's go back to the slides. All right, part C, if the water is not replenished, how long can this reservoir produce power at this rate? So the good news is, because you already found that piece of information out in part B, I already have the answer. So going back to the work here, we already found out how much time it'll last if I have this volume and it's being drained at that rate. So 8.5 times 10 to the 6 seconds. Now, you don't want to give your final answer like that, although that should be part of your calculation, because telling someone, well, this amount of energy is going to last you 8.5 times 10 to the 6 seconds. Most people are not going to be able to understand what that means. Okay, so we have to have a better unit to communicate that information. So let's see what better unit we can come up with. 8.5 times 10 to the 6 seconds. Let's start by converting that to minutes. Okay, so I know that 60 seconds is 1 minute, and I'm going to convert that to hours. I know 60 minutes is 1 hour. Okay, so let's see how many hours that comes to. That might be good. If not, we can convert it again. Seconds cancels with seconds, minutes cancels with minutes. So we take 8.5 times 10 to the 6 and we divide it by 60 times 60. So that's 2,361 hours about. That's a lot of hours, so let's convert that to days. Okay, 1 day is 24 hours, so H's cancel. So take that number and divide by 24. So that's about 98 days. So just over 3 months it'll last. Okay. So that's a nice way to express the answer for part C. All right, let's go back to the slides. Okay. Now, every type of energy we've looked at so far really at the end of the day relies on the sun. If you're looking at wind energy, that relies on the sun. As we saw in the beginning of 8.1, it is the sun's energy which drives convection currents and the wind, which is wind energy. Now, hydroelectric systems, how does that work? Well, after the water falls down, it's the sun's heat that has to evaporate that water and drop it back to a region of higher potential energy. So again, it uses the sun. Now, even though these forms of power use the sun's energy, we don't refer to them as solar energy. Solar energy is specifically a term used for something else. Okay, so solar energy means whatever electricity or whatever energy you get from the sun is directly transformed into electricity, and that's done using what's called a solar panel, or more commonly known as a photovoltaic cell. Okay, so that's what we're going to be looking at here. We're also going to take just a brief moment and look at something called a solar heating panel, also known as a radiant panel. Okay, so we'll see what that is as well. Okay, let's give this problem a try. The sun radiates energy at a rate of 3.9 times 10 to the 26 watts. What is the rate at which energy from the sun reaches the Earth if our orbital radius is 1.5 times 10 to the 11 meters? All right, so let's go back to our sheet here. All right. Okay, so we have this sun, and the sun is radiating energy in many different directions. Now, it's radiating that energy, and it's a power, even though we're not told it's power. The rate of energy transfer is power, and after all, it's given in watts. That's 3.90 times 10 to the 26 watts. Now, if you're really close to the sun, okay, just imagine that's an astronaut there. If you're really close to the sun, you're going to experience a very high intensity of that energy. And if you're further away, well, you experience less intensity. And the further you move away, the less that intensity becomes. And the way you can imagine this is, imagine this is the sun here, okay, and it's radiating energy. If you're very close to it, it will radiate energy into this sphere, okay, because we're assuming that it's radiating energy equally in all directions. So if you're somewhere along this sphere, which is the same distance, so if I have a person here at point A and then here at point B, they're both the same distance away from the sun, because the sphere means you're the same distance from that center point. Now, if I'm at this certain distance away from the sun, I experience a certain amount of, well, intensity. And if I'm further away from the sun, so if I'm at a bigger radius away from the sun, I will experience a different intensity. In fact, being at this larger circular radius, so let's say points C and D, even though points C and D experience the same intensity, it is significantly less than A and B, because now whatever energy the sun was radiating has to be spread out over an even larger sphere, right? The bigger the distance gets from the sun, the greater that area becomes, and the more the energy has to be spread out. So for this question, we're told that the Earth is at the orbital radius of, so imagine if that's the sun, and let's say the Earth is here, the Earth is at an orbital radius of 1.5 times 10 to the 11 meters. So that's information given to us in the question. We have to figure out what the intensity is. Now, way back, it's been several units since we studied this, but we learned that we can calculate the intensity as power per unit area. Now, the area at which this energy is being distributed is a sphere. Okay, so we can calculate that as P over 4 pi r squared. So 4 pi r squared is the area of a sphere, the surface area. Right, so power, okay, so we're looking for intensity. So power is this number right here, 3.90 times 10 to the 26 watts. And in the denominator, I have 4 pi r squared, and my r value is right there, 1.5 times 10 to the 11 meters. So grab your calculator. So 3.9 times 10 to the 26 divided by 4 pi times 1.5 times 10 to the 11 squared. Okay, so I'm getting an intensity of 1379.34 about, so I'm going to call that 1380. And the units are going to be watts per square meter. So there's the intensity where the Earth is. If you were closer, that number would be significantly higher. Okay, now something to keep in mind is that this is the amount of energy per second per square meter. If you wanted to know the total amount of power hitting any part of the Earth at any point in time, you would have to multiply by the square area, right? The area squared, or whatever area that is, of the region that you are inspecting. We'll look at how intensity varies based on region and area coming up in a few slides. Okay, let's go back to these slides. Okay. Explain why the solar intensity is different for different parts of the Earth. So we just found in the previous question that 1,380 joules per second are imparting every square meter of the Earth. Now, what we have to remember is that the Earth is not getting that radiation at exactly the same intensity at every part. And if it was, the temperature at every single part would be the same. So on your screen, you're going to see these 3 orange arrows. And what you should notice is that the arrow on the bottom, that is showing that 1,380 watts per square meter is impacting somewhere near the equator. Now, the equator is getting a high amount of intensity of that radiation. If you move a little bit higher up, that energy has to now be spread over a bit of a larger area because of the curvature of the Earth. The Earth is curving away from it. And if you go even higher up, the curvature increases so much more. And so that same intensity of 1,380 watts per square meter has to be spread over an even greater area. And if you look, it's over 2 times as long as what you have at the equator. And so this shows that because the intensity decreases at the pole, this is why your temperature is less. Well, at least this is one of the reasons why the temperature is less. Okay. Another reason why the temperature varies is because of seasons and the tilt of the Earth. And actually, it's the tilt of the Earth which also results in the difference in intensity. Something interesting to point out. If you remember from the simulation you did in Unit 4, Circular Motion and Gravitation, you were on the PhET website and you analyzed the ellipticity of the orbit. And you saw that there is some eccentricity. If the orbit is perfectly circular, you have an eccentricity value of 0. And if it is, well, if it is a perfect ellipse, it would be 1 if it's furthest away from a circle. Now, generally speaking, the orbits of planets around stars or moons around planets, they have an eccentricity value close to 0, but they are never exactly 0 because they're always orbiting at some ellipse. And what's even more interesting is that the Earth is not always the same distance away from the Sun. And that's one of the features of having an ellipse. Sometimes the Earth is closer and sometimes the Earth is further away. And what's interesting for us in the Northern Hemisphere is that the Earth is actually much closer in the wintertime. Now that might seem a little bit counterintuitive, right? So in the wintertime, so if we look at the slides, look at the picture on the right here. The Earth is bending away. You see this region on top where my mouse is motioning? This region on top, imagine this is the northern North America, let's say, okay, northern hemisphere. Notice that it's pointing away from the sun, but imagine that this distance is closer to the sun than the distance on the left. Okay, so this would be the Earth in its winter mode. So, for example, January, February. The reason, though, even though we're closer to the sun, the reason it's cooler is because the axis of the Earth is tilted away from the sun. All right, describing solar energy systems. So let's look at photovoltaic cells, okay, also known as solar panels. Now, you don't need to know too much about how this works. If you're really interested in this stuff, it's great. And you'll study more about this if you take materials engineering in university. Most universities offer this as a first-year course. And it's quite interesting to learn about how different materials behave when you impart different, well, especially with semiconductors, when you impart impurities to them. Okay, so I'm sure most of you have heard of Silicon Valley. And if you haven't heard of Silicon Valley, you've definitely seen silicon on the periodic table. Silicon is what's called a semiconductor. Okay, so it's in between those metals and non-metals. Now, silicon in its pure form is not conductive. So what engineers do and what scientists do is that they perform a process called doping. Now, doping will change not only the electrical properties of silicon, but it also changes the optical and structural properties. So the image you see on the bottom half of the screen here, it shows a semiconductor. So here's your silicon, but you also have these little impurities. You have phosphorus on the top and you have boron on the bottom. Now again, if you're really interested, there's two different types of these silicons now. You have an N-type and you have P-type. Okay. This is all extra information. All you really need to understand is that these photovoltaic cells are made up of a semiconductor called silicon, and they're doped with impurities like phosphorus and boron. If you're interested a bit more, this N-type, this means it's doped with phosphorus. That means you have one more electron, therefore it's negatively charged. With the P-type, it's doped with boron. That means you have one less electron than silicon, so you're positively charged. So one less electron, and here you have one more electron. Okay. Anyways, you don't worry about that. If you're a little bit lost at what I'm saying, just don't worry about it. If you're interested, study this further in university. Okay. All right, let's try this problem. A photovoltaic cell has an area of 1 square meter and an efficiency of 10.5%. Part A. If the cell is placed in a position where the sun's intensity is 1250 watts per square meter, what is the power output of the cell? Okay, so power output of the cell. We're given intensity. Now, we just did a problem that involved intensity, and we also needed area, and sure enough, we have the area. But keep in mind, this time we have to also take into account the efficiency. So let's go back to our page here. Okay. All right, so our photovoltaic cell, the area is 1 square centimeter. We have to change that to square meters, otherwise we can't use it in our calculation. In fact, I'm going to do that right now just to save some time before I write down the other pieces of information. All right, I know that 1 meter is 100 centimeters. This way I can get rid of my centimeters unit, but be careful because I have centimeters squared here and I have centimeters here. If I just multiply by this value, I'm still going to be left with centimeters, and then I'll have also meters as well. So what I want to do is put a square here. That way you have 1 meter squared over 100 centimeters also squared. Okay? So that way I can cancel out my centimeters squared unit. Now I'm just going to show you this. So 100 times 100, what do we have? We have 10,000, right? So in reality, what you're doing here is you have 1 square centimeter, and this is being multiplied by 1 square meter over 10,000 square centimeters. Okay, so this way your centimeters squared cancels out, and you take 1 and you divide it by this answer, 10,000. So 1 times 10 to the negative 4 is what we have. 1 times 10 to the negative 4 square meters. And as you would expect, this number had to have gotten smaller. All right, so there's my area. I'm also told that my intensity is 1250 watts per square meter. I am told that the efficiency of the cell is 10.5%. That's pretty low, but not uncommon. 10.5%. What is the power output of the cell? All right. So based on the problem we just did, we saw that we can find a relationship between power, intensity, and area. So if I rearrange this for power, I'm going to have power is equal to intensity times area. So power is equal to I times A. But we have to remember that it's not that simple. The question asks for the power output of the cell, not what power it should be able to generate. The reason we're asking for the power output is because some of the energy is lost due to this lack of efficiency here. So whatever I calculate here, I know that only 10.5% of that is being useful. So when I take this value, I have to multiply by 10.5%. To get my true value. So intensity is 1250 watts per square meter. Area is, and I just found that's right here, 1 times 10 to the minus 4 square meters. And if you multiply by 10.5%, that means you're multiplying by the number 0.105. All right, so 1250 times 1 times 10 to the minus 4 times 0.105. Okay, so we end up with 0.0131 watts. All right, so that is how much power each cell generates. So this is the power output per cell. All right, let's go back to the slides. Part B, if the cell is rated at 0.500 volts, what is its current output? Okay, so if you're looking at that question saying, how am I supposed to find that? Well, you won't be alone because it's been a while since you did this. We have power. We just found it in part A. And now you're given voltage. How do you find current? Okay, so again, here's the power we just found. So part B, we know that P is equal to 0.0131 watts. We're told in the question that it's rated at 0.500 volts and we need I. Okay, so maybe when you see, the three of them written together like that, it'll jog your memory a bit. Okay, if it doesn't, if you don't remember, oh, sorry guys, this keeps coming out of focus. Let me try, okay. Let me see if I can locate my formula sheet and see if I can find that formula to show you in case you forgot. All right, so in your formula booklet, what you want to do is look at box 5.2. And in box 5.2, there's a formula in about the middle. It's P is equal to V times I. I wonder if I can hold this a bit closer. Hopefully you can see that there. P is equal to V times I. That's the one you're going to use. Power is equal to the product of voltage and current. And that's really all it is. So we're looking for current actually. So let's rearrange. So I is equal to P divided by V. So 0.0131 watts divided by 0.500 volts. So 0.0131 divided by 0.5. So that's 0.0262 and units, amperes. All right, so that is the current per cell. Going back to the slides. Oh, sorry guys. Part C, if 10 of these cells are placed in series, what will the voltage and the current be? So again, this requires you to remember stuff about electrical circuits from grade 11. When you have loads in a circuit placed in series, there are certain attributes that affect the current and the voltage, and that's different than when you have a parallel circuit. We're not going to be considering mixed circuits here, although it should be okay to do that as well. But if you have a series circuit, so something that you probably saw in grade 11 was like this. So you have your battery, there's your minus and your plus, and let's say you have 3 lamps connected in series. I know that whatever voltage I have at the source, Vt, which we also called epsilon, the electromotive force, that has to be dropped over all three of these combined. So if I have lamp 1, lamp 2, and lamp 3, and they have associated voltages V1, V2, and V3, the sum of the voltages has to equal the electromotive force out of the battery. So V1, V2, and V3 has to equal epsilon. But the current coming out of the battery, and again, unfortunately, we have to draw the current going clockwise here, even though it's actually going counterclockwise. Whatever current is going through the battery is the same current that goes through load 1, load 2, and load 3, and at any point in the circuit, it'll be the same. So what's the current if you have 10 of these placed in series? So if you have 10 cells placed in series, so I'm not going to draw 10, but imagine that there are 10 here, and they're all placed back to back. Okay, so what's going to happen? The current is going to be the same. The current still has to be 0.0262 amps. Now, what's different is the voltage. Like I said, in a series circuit, you have V1 plus V2 plus V3 is equal to the total voltage. So if I know that each cell has a voltage output of 0.5 volts, then that means I have a total voltage of 10 of those. So 10 times 0.500 volts, which is just 5 volts. All right. Oh, let me just box this as well. All right, going back to the slides. Okay, so on the slides, it's just stated in words. In series, the voltage increases. In series, the current stays the same. And there you have your values. You have your 5 volts, and you have your original current. Okay, part D. If 10 of these cells are placed in parallel, what will the voltage and the current be? All right, going back to our page. Same idea, except this time we're putting them in parallel. All right, so that means you have, well, you've got one piece here, and that's connected in parallel to another piece, which is connected in parallel to another piece. And this continues, well, until you have 10. So you have 10 connected in parallel. Now, when you have resistors or loads, whatever it is, connected in parallel, whatever current comes in from the battery, it has to split. So let's say you have some kind of a battery source here. That current has to split amongst the 10 loads. So my current is going to be 1/10. So across each cell, it's going to be 1/10 of the 0.0262 amps. So this thing divided by 10, if you divide this by 10, it's going to get smaller by one more spot, right? So if we take that divide by 10, instead of 2.62 times 10 to the minus 2, well, it'll be 2.62, well, in this case, 0.0262 divided by 10. Okay, so 2.62 times 10 to the minus 3. Hang on, guys. No, I'm sorry. Each one of them has this current going through it. So that means we actually have to take this and multiply it by 10. My apologies. Okay, yeah, each one takes this current. So if you have 10 of them, then that means you have, well, 10 times the current, right? Before we had the current staying the same. This time we have more current. So 10 times 0.0262. Okay, so that's simple. What am I doing? 0.262 amperes. All right. Now for the voltage, when you have a parallel circuit, the voltage is going to remain the same. All right, so whatever voltage I had originally, which was 0.500 volts, that's going to be the voltage across each resistor, or in this case, each cell. Okay, going back to the slides. Part E, how many cells would you need to operate a 100-watt circuit? Okay. Well, going back to the page here. Well, what we found in, where was it? In part A, we saw that the power output per cell was 0.0131 watts. So if we want to generate 100 watts, and we know that this is how many watts you get per cell, well, you just have to divide those two numbers to see how many cells you're going to need. Okay, so part E, so call power is 0.0131 watts per cell, and I need 100 watts. So if I take 100 watts and I divide it by 0.0131 watts per cell, I'll get the number of cells. All right, so 100 divided by 0.0131. So that's about 7634. 7634 cells. Okay, that's a lot of cells. All right, let's go back. Hey, now those of you using a calculator, you'll notice that you have little solar panels at the top, and usually these kind of devices work with a combination of battery with backup solar power. All right. Okay, moving into the last series of problems. A photovoltaic cell of area 6.5 times 10 to the minus 4 square meters is situated on the roof of a house. The cell has an efficiency of 8%. At a time when the power of the solar radiation incident on the photovoltaic cell is a maximum, the cell delivers a power of 47 milliwatts to the external circuit. Deduce that the maximum value of the power of solar radiation incident on the cell is approximately 0.9 kilowatts per square meter. Okay, that's a lot of information. We want to find the maximum power of solar radiation. We have to show that it's this value. Whenever a question tells you to deduce something, that means you cannot use this value anywhere in your calculation. It has to come out of a calculation involving other values. But you cannot plug this in and show that you're getting what's given. You have to use what's given to show that you're getting 0.9. Okay, now, you know the square area of the cell. Okay, you know the area of the cell, 6.5 times 10 to the minus 4 meters squared. Let's see here. The last piece of information here, the cell delivers 47 milliwatts of power. So that is power. You have area. How do we show that it's actually this value? Well, if it's able to deliver this much power to the external circuit, this is after energy is lost, right? So after this photovoltaic cell takes in energy from the sun, after some energy is lost, perhaps due to resistance, some sort of friction, it's going to result in 47 milliwatts, right? So it's only 8% efficient. So 8% of the total power is 47 milliwatts, even though if it was ideal, it would be able to produce much more. So let's go to our page here. So I know that 8% of some power, and that would be the input power, results in the output power. And the output power is 47 milliwatts, also known as 47 times 10 to the minus 3 watts. So if 0.08, so 8% of Pn is equal to 47 times 10 to the minus 3 watts, well, that means Pn is going to be 47 times 10 to the minus 3 watts divided by 0.08. So grab your calculator. 47 times 10 to the minus 3 divided by 0.08. So 0.5875. So this is in fact how much energy is, or how much power is actually generated. Okay, so how do we get the value in the question? The value in the question is 0.9 kilowatts per square meter. Well, you're going to need the area, right? So the area is given to us in the first line of the question, and that's 6.5 times 10 to the minus 4 meters squared. So if I take this wattage, I divide by this area, I'm going to have intensity, and that's what we're looking for. So intensity is power per unit area. So 0.5875 watts divided by 6.5 times 10 to the minus 4 square meters. So taking that number, divide by 6.5 times 10 to the minus 4. So that's 900, it's about 904. 904 watts per square meter. Now in the question, it's given in kilowatts. So if I want to give this in terms of kilowatts, I have to divide by 1,000. So that's the same thing as if I divide by 1,000, 1,000 has 3 zeros. I would take the original decimal and move it to the left 3 spaces. 1, 2, 3. So that becomes 0.904 kilowatts per square meter. And sure enough, that is the value that we are expected to get in the question. Okay, so that's what we have shown. The exact number of sig figs, well, that's based on the amount of sig figs in the question. 6.5 has 2 sig figs, 47 has 2 sig figs, 8%, the efficiency percentage does not contribute to the number of sig figs. All right, so going back here, we're going to round this to 2 sig figs, so 0.90 kilowatts per square meter. And there's our final answer for part I. All right, going back to the slides. Part II. State one reason why the power of solar radiation at any particular region does not have a constant value. So this is a good time for me to point out that there are going to be a lot of you that try to answer this question and will unfortunately make a very common mistake. Okay, so having knowledge is not the same thing as understanding where to apply it. So you know, based on what we've seen in this lesson, that based on the curvature of the Earth and based on how the intensity of radiation from the sun hits the Earth, that intensity changes over different regions of the Earth. So we saw that at the equator, there's a very high intensity of radiation because that energy is concentrated over a smaller area. But as you move northward toward the poles, or even southward technically, but north we have more land than water. If you move northward, that intensity gets spread out over a larger area, and so it decreases that much more. Okay. Now, this question specifically says, state one reason why the power of solar radiation at any particular region does not have a constant value. So this question already assumes that you're in one region. So stating that because the curvature is different in different parts of the Earth results in different power per unit area will get you 0 marks for this question. If you're already in a particular region, how can the power vary? Well, think about that for a moment. When you're sitting in your room, you're looking outside, you're looking at the sky. Well, the radiation is coming in through the atmosphere, it's coming in through the sky. What do you notice when you look outside through different parts of the day? Well, there might be different amounts of cloud cover. Clouds can reflect a lot of sunlight back into outer space. So cloud cover varies, that's a significant reason. Seasons changing is another reason, and that has to do with weather patterns, which again relate to clouds and their density. Okay, so just be careful with your answer to the question. So what I explained first is what is outlined in the FYI box in red at the bottom of the slide. Okay, moving on. Draw a Sankey diagram for a photovoltaic cell having an efficiency of 18%. Probably the most detailed Sankey diagram that we saw was that of a nuclear power plant. This type of energy transformation we're not looking into in as much detail. So what you really have to concern yourself with is that the energy in the incident sunlight gets produced into electricity. Now, from the examples you've seen, that efficiency is quite low, which is why that width of the usable electricity arrow is so much smaller than the wasted heat. Now, of course, there are so many other energy transformations that can take place within the cell itself. We are not going to be getting into that right now, but just understand that it actually does exist. Okay, now I did mention that we're going to be talking about heating panels, and this is the slide where we're going to do it. A heating panel is exactly what it sounds like. It is a flat surface or a panel that produces heat, infrared radiation. Okay, so sometimes these things are called radiant panels, or sometimes they're called far infrared radiation. Okay? So infrared radiation means heat. This heat comes from the sun. And so this is essentially how they're built. After having a layer of insulation, on top of that you have something that can absorb the radiation. On top of that you have pipes, and inside of these pipes water runs. Now, If you have a piece of glass on top of that, the energy from the sun moves through the glass, it gets concentrated and heats up the water inside of the pipes. When the water heats up, that energy can then be absorbed into the black absorber, thereby heating up the room. Now, you can also use these kinds of panels using the same idea to cool a room. We're not going to be looking into the cooling panels, but this is how a heating panel works. Now, if you can imagine, if the water moves slower, it has the ability and time to absorb more sunlight and more heat. So if the water moves through the pipe slower, it will be able to release more energy to the room. And that is the extent at which we're going to be looking at heating panels. What you really need to concern yourself with is the solar photovoltaic cells. All right. This question is about solar heaters. All right, an active solar heater, also known as a solar panel, is installed on the roof of a building in the southern hemisphere. Suggest why the panel should be facing northwards at noon. All right, if you're in the southern hemisphere, you know, based on what we've seen in all these diagrams, that the highest intensity of radiation is hitting the Earth at the equator. So if you're in the south, you want to face that solar panel towards the equator. In other words, you have to face it north. If you are in the northern hemisphere, you have to face that solar panel south to get the highest intensity of radiation. And so that's all this question is looking at. Okay. The last question is a bit of a long calculation question. At one particular location, the average power received from the sun during a 6-hour period each day is 840 watts per square meter. The solar heater has an overall efficiency of 35%. It is required that during the 6-hour period, the solar heater raises the temperature of 140 kilograms of water by 25 Kelvin. The specific heat capacity of water is 4.2 kilojoules per kilogram per Kelvin. Calculate the minimum effective area of the solar heater. There is a lot of information in this question, and if you're looking at that a little bit stumped, because sure enough, there is thermal energy physics once again, just take a moment, pause the video, read through the question a couple times, make sure you understand what is happening so that you can start to formulate a clear and decisive way of tackling this problem. Okay, so we'll resume in a moment. Okay. So let's now go to our page. Hopefully you have the slides in front of you with the question. All right. So at one particular location, the average power received from the sun during a 6-hour window is 840 watts per square meter. Now I have to tell you to urge caution here. The question tells you that this is power, but this is watts per square meter. You know that power is only measured in watts. Watts per square meter is telling you that this is not power, it is an intensity. Okay, so be careful. Even if the question says power, it says average power. So power per what? Well, it's power per area. Right, so be careful. So that's the intensity. The solar heater has an overall efficiency, so percent efficiency of 35%. That's not bad compared to what we've seen before. During the 6-hour period, so the time interval here is 6 hours. Now, whatever's happening in the rest of the question, I know that in order to use this piece of information, I have to convert it to an SI unit. So I'm going to do that right now. Okay, so 6 hours, I know that 1 hour is 60 minutes and 1 minute is 60 seconds. So I'm canceling out my undesired units. So here I have 6 times 60 times 60. So that's 21,600 seconds. All right. Now, during this time, the solar heater raises the temperature of 140 kilograms of water, that's mass, by 25 Kelvin. And I'm even told the specific heat capacity of water, 4.2 kilojoules per kilogram per Kelvin. Okay. These three things together should remind you of another quantity. M, C, and T. Of course, usually we didn't see it as T, we saw it as delta T, the change in temperature. all three of these things allow us to calculate a value known as Q. Q is the energy. Okay, so if we know energy, there is a way for me to figure out power, and power is related through intensity with area, and hence I'll find the area, having taken into account the efficiency as well. All right, now be careful when you're calculating Q, because the C is given in kilojoules. Right? Kilograms is okay, that's the SI unit for mass, but kilojoules is not. You need this to be in joules. All right, so this is, so if it's kilo, that means it's 4.2 times 10 to the 3 joules per kilogram per Kelvin. Okay, so that's what we're going to use. So Q is equal to MC delta T. I really hope that formula is familiar to you. So 140 times C, that's 4.2 times 10 to the 3. And it's also per Kelvin, so keeping this in Kelvin is fine. But remember, for this unit, a change of 25 Kelvin is the same as a change in 25 degrees Celsius. The change is the same. The specific values are different. Okay, 140 times, so let's do it like this, 140 times 4.2 times 10 to the 3 times 25. We have 1.47 times 10 to the 367. All right, so that's how much energy is delivered. Now, that energy is delivered over a certain period of time, right? So that's 21,600 seconds. So the power that ideally should be delivered, right? So, well, we're told actually, hang on, this is actually not the power ideally delivered. It is the power actually delivered. The question tells us that due to this solar heater, it's able to actually raise the temperature of the water by 25 Kelvin. So that means that the power output is what we're calculating, not input, output, since this is what it's actually capable of doing, not what it's theoretically able to do. So power is energy per unit time. And the energy in this question is given by Q. So Q over T. So we have 1.47 times 10 to the 7 joules divided by time, and there it is, 21,600 seconds. So we have 1.47 times 10 to the 7 divided by 21,600. So 680.56 joules per second, also known as watts. All right, so we have that. Given that value, so we have energy per unit time. How much energy went in? The amount of energy that went in, the amount of power that went in is related to the area of the solar heater or of the solar panel. It's the efficiency which causes it to be lost and decreased to this amount. So I know that 35% of the input power becomes 680.56, which is the output power. So 0.35 times P in is equal to 680.56. So that means that P in is equal to 680.56 divided by 0.35. So let's figure out what that input power was. 680.56 divided by 0.35, and we get 1944 watts approximately. Okay, so there it is, 1944 watts. All right. Now, I know that the average power, also known as the intensity, received from the sun at that location is 840 watts per square meter. So I'm going to need to use that in conjunction with the power I just calculated that it takes in to figure out what the area is. So intensity I know is power per unit area. So therefore, area is equal to power divided by intensity. So 1944 watts divided by 840 watts per square meter. Okay, so looking at the units, you can also see that we're going to get square meters out. So 1944 divided by 840, we get 2.3 square meters. So that means that the area of the solar panel is 2.3 meters squared. Okay, so that marks the end of lesson 8.1 in its entirety. So 8.1 energy sources is done, and so is video 404. Stay tuned next time for videos on section 8.2.